now going to be going to a quick commercial break. Do not forget, guys, I'm still emphasizing those SMSs. 41580 is, of course, our SMS number. Then you guys can just SMS through any questions and we will answer them in studio. Right now, though, we're going for a quick commercial break. We'll see you in a bit.
Picture tells 1,000 words. We tell even more. It's mind-blowing documentaries every Tuesday at 9, exclusive to Mzansi's official storyteller, SABC 1. Mzansi for sure.
Welcome back, everyone. Now, before we get straight into another revision session, we got Desiree from Pretoria on the line. Hi, Desiree.
Hi, Amanda.
Do you have your physical science question ready?
Yes.
Okay, ask away.
The statement 2 NaCl in bracket AQ plus 2H2O in bracket I arrow 2H gas plus Cl2 gas plus 2 NaOH in bracket AQ. The question is, calculate the standard electrode potential for the given equation.
All right, now I didn't write those down, but all right, what we've got to do there, Desiree, by the way, Desiree, how was your physical science paper 1 this morning?
Good.
Was it good? Did you really enjoy it? Do you think you did well?
Yes.
I'm thrilled to hear that. Okay, Desiree, I'm not going to do your question, but I will tell you how to go about answering it. You've been given a complete equation there. Now, what you've got to do is you've got to reduce that to 2 half reactions. Now, it sounds like you've got NaCl involved there, and you've got NaOH involved there. It sounds like the kind of equation that we're probably going to do on a later question there, but if you divide those two into 2 half cells, one of those half cells you're going to find, one of the half reactions, I beg your pardon, you're going to find that electrons will be lost. In other words, electrons are going to be released. That will be the oxidation half of the half reaction. And for that, you will be able to look at your table and get a value for the electrode potential. You've then got another half reaction, you'll be able to do the same thing there. Now, if, and you know this little trick, let's just have a look on the overhead. Let's just have a look here, and I want to show you something. Let's say we've got, the one was it sodium up here? You had sodium, and then you had chlorine, which is further down here somewhere, right down at the bottom of the table. Now, if you've got sodium reacting with chlorine, then if you can draw a C, and this is for table 4B, remember. This is for table 4B in particular. If you can draw a C to say, these are my reactants, and here are my products. If I draw a C like that, then the reaction is going to be spontaneous. Okay? And when you know the values of the half reaction potentials, you will be able to work out what the EMF is for that reaction. And you could actually create an electrochemical cell using those 2 half reactions. Okay, I haven't answered your question completely because I didn't hear it perfectly, but there is the principle of working it out, and I hope that we may do one of these just now if we have time. Okay, Desiree?
Yes.
All right, wonderful, Desiree. Now, we've got another caller on the line. We've got Matapelo from Mokopane. Hello, Matapelo.
Hello. I've got a question in extraction of aluminium.
Okay.
I'd say, name 2 advantages and disadvantages of aluminium environment.
Okay. Matapelo.
Matapelo.
Matapelo. Matapelo, you quickly. How was your paper 1?
Hello?
How was your paper 1 this morning?
Oh, it was fine. I love it.
Good. Oh, I'm pleased to hear that. Okay. The advantages and disadvantages, the upsides and downsides of aluminium. Look, aluminium is a very useful metal. We use it all over the place. But the one thing about aluminium, it is very reactive. And therefore, when it reacts with oxygen, it forms a very, very strong bond with oxygen. And therefore, we have to use a lot of energy to break it apart to get our pure aluminium. Where does that energy come from? It comes from electricity. And the electricity required to purify aluminium, we need large amounts of electricity. This is why some of the more successful aluminium refining is in places like Canada, where you have a lot of hydroelectricity from the snow melting, the water rushing by, giving us good electrical energy, and there you will find your big aluminium smelters. Now, we've got, not smelters, but refineries. We've got this down at Richards Bay, but we have to supply that electricity by burning coal. So there is one of the big advantages, or disadvantages, if you like, of the aluminium refining process. It's energetically very costly. Okay? Does that give you something to go on?
Yes.
Okay. Thanks very much. I think we've got another one rolling in.
Yep, that was Matapelo from Mabupane. And then we've got another caller right now from KZN. We're going to be talking to Thokozane right now. Hi, Thokozane.
Hi, I'm fine.
Okay, ask your question.
So my question says, I want to know what's happening if, between electrolytic cells, so when increased electrolytic cells in the peak and the cathode, or so I want to, what is?
I'm sorry, I'm not hearing that. Can we just try that one again?
Okay, my question says, what is effect on the potential difference if increasing the electrolytic cell or decreasing?
I'm just wondering if this isn't the question that I answered a little earlier. Maybe you weren't listening, maybe you were waiting on the phone. When you have, and I'm assuming this is what you're asking, when you have an electrochemical cell and you have your concentrations of the electrolytes in the two halves of the cell, when they're in standard conditions, in other words, when the concentrations are 1 mole per cubic decimeter and all other things are correct, you've got the right temperature, if they're gases, they're at the right pressure, then you get a cell EMF, which you can work out by looking at your table. But as the reaction goes ahead, as it proceeds, what we find is the concentrations of the electrolytes will change. In the, let's see, in the anode half, where we're getting oxidation taking place, we are going to find more ions going into solution, and therefore the concentration will increase. In the other one, the concentration of the ions is going to decrease, and there we get what's called a back potential, which works against the cell potential. And eventually, when the back potential is equal to the cell potential, the sum of those two things is 0, and the cell stops working, and we've got, as I say, a flat battery.
All right, I'm
Okay?
sure
that does it for you.
I'm sure it does answer Thokozani's question. But right now, though, I think within around about a minute and a half that we've got, we can get into...
Let me get into the next question. Okay, what I'll do now is we'll do question 12 of the supplementary paper of 2009. Let's read through it. We've got time to do that. About 1/3 of the protein consumed by humans comes from fertilizers. Now, that doesn't mean we're eating fertilizers. It means we use the fertilizer to give us the food that we need to get the protein.
I got scared for a
Let's be clear
minute.
about that. Okay, the flow diagram below shows the industrial processes A, B, and C in the production of fertilizers. Let's have a look. Now, what we've got here is very clearly that's going to have something to do with ammonia. I'm starting to realize, well, I realized that as soon as